In this section, we're going to look at uniformly accelerated motion. Uniformly accelerated motion is motion with constant acceleration. So acceleration is a constant for this kind of motion. In other words, the rate of change of velocity with time is constant. The velocity is increasing or decreasing at a constant rate. Now, if the acceleration is a constant, then average acceleration and instantaneous acceleration are going to be equal. So we have instantaneous acceleration equals average acceleration, but average acceleration, if you remember, is change in velocity per unit time, which is final velocity minus initial velocity divided by time. Okay, so from this equation we get Vf minus Pi, that's final velocity minus initial velocity, equals acceleration times time, but this is customarily written as final velocity equals initial velocity plus acceleration times time. This is one of the equations you can use for uniformly accelerated motion. Final velocity equals initial velocity plus acceleration times time. To find another equation, we're going to use the graph of velocity versus time. Suppose this is the graph of velocity versus time. This is velocity, this is time. Now remember, since acceleration is a constant, the graph of velocity versus time is going to be constant, because acceleration is basically slope for a graph of velocity versus time. Suppose now the velocity increases from Vi to Vf, let's say in a time interval t. Okay, so starting here, and then at t, the velocity will be over here. So the graph of velocity versus time is a straight line joining these 2 points, because acceleration is a constant. Now if you remember, displacement can be obtained from a graph of velocity versus time at the area enclosed between the velocity versus time curve and the time axis. So in this case, the displacement actually equals to this area. Okay, now we can calculate this area by using the formula for a trapezoid, but probably it's easier to divide it into a rectangle and a triangle. Okay, so this one is Vf minus Vi, this minus this, and this interval over is time, and this one is Vi. So we can calculate the displacement at the sum of the areas of this rectangle and this triangle. So you can say delta x equals the area of this rectangle over here, whose base is t and whose height is Vi, and then plus the area of this triangle over here, and this triangle over here. Its base is t, its height, the height of this triangle over here, is Vf minus Pi. Okay, so this equals the area of this rectangle is Pi times t, that is length times width, and for this one it's going to be half base times height, so you've got t, and then the height is Vf minus Pi. Okay, but from this formula over here, we see that Vf, the difference between the velocities, actually equals acceleration times time. Okay, so we're going to make that substitution. So we have delta x equals Vit plus half t, substituting Vf minus Vi by At. We have the following. So delta x equals initial velocity times time plus half acceleration times time squared. So this is another equation we can use for a uniformly accelerated motion. These are the only two independent equations we have for a uniformly accelerated motion. So that means you can solve only for two variables at a time. But we can also obtain other dependent equations in terms of other variables. So let's try to do that. First, let's look at average velocity. By definition, average velocity is displacement divided by time, right? But we just conclude that displacement is given by this expression. So we can say displacement equals VIT plus half a t squared divided by the time. Okay, that gives us VI plus half a t. Again, remember, VF minus VI equals acceleration times time. So I can replace this one by BF minus VI. Okay, with that we have the following: average velocity equals VI plus half of BF minus VI. Okay, let's combine these expressions with common denominator 2. So you've got 2VI plus BF minus VI. So you get average velocity for a uniformly accelerated motion is simply the average of the initial velocity and the final velocity. Okay, this equation might look like it's valid for any kind of motion, but it's valid only if the acceleration is a constant, if the velocity is increasing or decreasing at a constant rate. Now let's try to get another dependent formula. If you remember, we have the following formula: v bar, or average velocity, equals delta x divided by time. Okay, so we have displacement equals average velocity times time. Now we can substitute for the average velocity. So we've got average velocity equals VI plus PF over 2 times t. So this is one of the equations you can use for this kind of motion. Okay, and we can obtain another dependent equation by substituting for this one. You remember, VF equals VI plus 80. From this formula we can get time equals VF minus VI divided by A. So we can simplify this expression to VI plus VF over 2 times VF minus VI divided by A. Okay, now let's multiply this. This is a product of sum and difference. Okay, you remember this formula from algebra: A plus B, A minus B equals A squared minus B squared. Okay, applying this formula we get delta x equals VF squared minus VI squared divided by 2A. So we have VF squared minus VI squared equals 2A times delta x, but this is customarily written as the square of the final velocity equals the square of the initial velocity plus 2 times acceleration times delta x. So this is another equation you can use for a uniformly accelerated motion. Okay, so let's put these equations together. Equations of a uniformly accelerated motion. Uniformly accelerated motion. Accelerated motion. These are: final velocity equals initial velocity plus acceleration times time, and then displacement equals initial velocity times time plus half times acceleration times the square of the time. And then we have VF squared equals initial velocity squared plus 2A times delta x, and then we have delta x equals VI plus VF over 2 times time. These are the 4 equations you can use for a uniformly accelerated motion. If you know you're dealing with a problem where the acceleration is a constant or where the velocity is changing at a constant rate, you can use any of these equations to solve the problem. Now, there are five variables in this 4 equations. They are the initial velocity, the final velocity, acceleration, time, and delta x. But as I have mentioned before, the only independent equations among these 4 equations are these two. Okay, these 2 equations are dependent equations. They're included only to make it easier to solve problems. So that means you can solve only for 2 variables. Since we have only 2 independent equations, you can only solve for 2 variables. So you can say that if you know any 3 of this, you can solve for the other 2. So if you know any 3 of these variables, you can solve for the other 2. You can solve for the other 2. Okay, so when you solve problems like this, you have to make sure you know 3 of these variables before you can solve the problem. Okay, now when you use these equations, it's very important that you know whether they're positive or negative. Okay, so remember, velocity is positive if the particle is moving to the right, negative if the particle is moving to the left. Okay, so we have the following sign conventions for velocity. Okay, positive if moving to the right, and negative if moving to the left. Okay, so these are the sign conventions for velocity. The velocity should be taken to be positive if the particle is moving to the right. It should be taken to be negative if the particle is moving to the left. The same thing about displacement. Okay, it's going to be positive if moving to the right, and it's going to be negative if moving to the left. Okay, time is always positive, and acceleration is positive. Acceleration is positive if velocity is increasing, and negative if velocity is decreasing. But time is always positive. So you should be careful with the sign conventions when you solve problems like this. Now let's consider an example. Let's say a car initially moving with a speed, let's say, of 20 meters per second, will stop it in a distance of 100 meters by applying the brakes. Okay, so let's try to solve number 1, acceleration. Let's calculate the acceleration of this motion. Okay, so we're looking for A, and let's state what we know. You see a car initial moving with a speed of 20 meters per second. That means the initial speed is 20 meters per second. And then we're told you will stop it. Stop it means the speed is 0, and a distance of 100 meters. So the final speed is 0 because it stopped, and this happened in a distance of 100 meters. Okay? So now we have to select the suitable equations from the 4 equations. Okay? The suitable equation is the equation involving these 4 variables. Okay? So if you know this, we can solve for that variable. Now if you look at this equations, you see, look at this problem. We have final speed, we have initial speed, we have delta x. We can solve for acceleration from this equation. So we're going to use the third equation over here to solve the problem. So we're going to use this equation, vf squared equals vi squared plus 2 times acceleration times delta x. Okay, the final speed is 0, the initial speed is 20, then plus 2 times acceleration, and delta x is 100. Okay, so we have negative 400 equals 200 times acceleration. It follows acceleration equals negative 2 meters per second squared. Why is it negative? The acceleration is negative because the velocity is decreasing. Okay. Next, we can calculate the time taken. Number 2. Let's calculate the time taken during this motion. Okay. Now, since we know 4 of the variables, you can basically use any equation to solve for the time. Probably the easiest equation to use would be the first equation. You see, this equation over here. We know VF, we know VI, we know A. We can solve for T. Okay. So we're looking for T, and then VF equals VI plus AT. The final velocity is 0. The initial velocity is t, and the acceleration is negative 2 times time. Okay, so we've got negative 20 equals negative 2 times time. That gives us t equals 10 seconds. Now remember, time is always positive. Time moves forward, it doesn't go backward. So if when you solve problems like this, you get negative for the time, you should know you're doing something wrong. So you see, we have 5 variables, we're given 3 of them, and using the equations of a uniformly accelerated motion, we're able to solve for the other 2 variables.